In this example, we're given this simple single loop circuit that contains a current source and a 0.2 microfarad capacitor. And this time we are given what the current source is providing, and the current source is a function of time and it's changing in time depending on the time. Actually, it's different ranges. So before 0 it's 0, between 0 to 20 microseconds it's providing some sort of a linear current, and then it basically goes all the way, and you'll see it goes to 0 after 40 microseconds. And what we're being asked to compute is the voltage here, the power, and the energy. And I have went ahead and I just basically wrote these equations in here so we can use them. So we will not be using this because we already have the I, so what we're looking for is the voltage. And I'm also given some sort of an assumption here, and that the reason for this assumption will become clear in a second. So what we're looking for is the use of this equation in here. That's what we're looking for. So of course passive sign convention applies. So what we will assume is the following: that the voltage across the capacitor looks something like this. So the current coming from the current source is actually going that way, and of course both of them are a function of time. Okay, so if we assuming passive sign convention, the current is hitting the positive, that means we're going to have to use the positive. Good. All right, so we don't have to worry about the negative anywhere. And now let's talk a little bit about this assumption here. So the equation tells me that you have to consider what we call the initial voltage. So initially, before t equals 0, what this tells me is there was no voltage. Basically, there's no energy stored in that capacitor. So we can substitute Vt of 0. Well, a couple of things. We can say that T0 is just simply 0, and V of T0, which is V0, is just simply 0. So the voltage initially stored at this capacitor is 0. So we start after the 0. That's what we have. So technically, in this equation, we don't need to use this part. All right, so that leaves us with just the integral in here. That's all we need to do. Okay, so let's do these integrals in here, and of course we're going to have to do several integrals because we have different ranges. We have one here, one here, one here, and one here. So technically we need to do a couple of integrals in here because the integral of 0 is just simply 0. Okay, so let's do this here. So for the range, I'm going to just stop basically for t is less than 0. Well, let's compute. What we're looking for is the v. So v is simply, well, the integral of 0 is just 0, so I'm just going to say that's 0. So let me just keep track in here and just basically keep track of what v of t is in here. So v of t, we're looking at it right now, it's actually 0 for t is less than or equal to 0. All right, let's focus on the second range in here, which is basically t is between 0 to 20 microseconds. So what we need to do in here, and I'm just going to say, well, t is between 0 all the way to 20 microseconds. Okay, so what we need to do is, in order for us to figure out what v of t in this particular range, we need to do 1 divided by c, and c is just simply 0.2 times 10 to the negative 6 farads. Okay, and what we do is we integrated t0, in our case is just simply 0, all the way to t, I of t, which happened to be 5,000. And we don't use t in here, we're going to be using tau. We change the variable so that we don't confuse it with this particular one in here. Okay, so we can do this here, d of tau. But of course, in this particular case, well, we're going to keep it as t because it's all the way 0 to 20. We're not integrating to 20, we're integrating to t because we want an equation in terms of t. That's what we want. And of course, plus 0 because the initial voltage is 0. All right. So what we have is 1 divided by that will be 5 times 10 to the power 6. And then we have 5,000, and I believe tau is basically just simply tau squared divided by 2, and this will be 0 to t. All right, and that will become just simply 1.25 times 10 to the power 10 of t squared, because t squared minus 0 of t squared. So that's what we have. So we're going to write it in here, 1.25 times 10 to the power 10 t squared, and that's basically for t is between 0 all the way to 20 milliseconds. Okay. Microsecond, sorry. So again, you don't put the microsecond or the 20 in here because this isn't what you're trying to do. What you're trying to do is you're trying to get an equation in terms of t. That's what we want. We know that it stops at 20 microseconds. All right, we continue. So we figured out the voltage in this range. So what we need to do is we need to figure out the voltage in 20 to 40. Okay, so I'll just write it in here in a different color. So what we have is t is between 20 microseconds all the way to 40 microseconds. So what we have is we need to do v of t is just simply 1 divided by 0.2 times 10 to the power negative 6. And now what we integrate is 20 this time, all the way also to t. And then what we have is we have this equation in here, which is 0.2 minus 5,000 t. That's in amps in here. This is coming from here. And of course, because we're using t in the limits of the integral, I'm going to change the variable in here. So instead of t, I'm going to be using tau, and that's d of tau. Okay, so we do, and of course plus 0 because initial voltage, actually the initial voltage now is not 0, because what happens now is we have a voltage. So what we need to do is we need to go back to the previous equation in here, okay, and just figure out in this particular case at V equals 20, what is the value of that voltage in here. So the value of that voltage is just simply 5 times 10 to the power 6, 5,000, well, let me rewrite it because we computed that equation in here. Okay, so that will be just simply 1.25 times 10 to the power 10, and then here what we have is 20, and this is in microseconds, so I'm going to multiply by 10 to the negative 6 to get from microseconds to seconds, and I'm going to take it to the square, and that will give me the exact value in volts. And that would be exactly 5 volts. In this particular case, we don't put plus 0 in here. What we do is we put plus 5 because this is coming from the previous stage. So what happens is now we're using the same equations that we have been using, okay, but now the initial voltage in here, because we waited from 0 to 20 microseconds, we provided some sort of a current, so a voltage got built up on top of it, and that exact voltage happened to be 5 volts based on this particular equation. So we got an equation, and what I did is I just went and I substituted 20 in here just to figure out exactly at 20 milliseconds what's the voltage in here. And for that particular case, I assumed it is the initial case. Okay, this is basically my t0 now is 20, and I will use the 5 in here. All right, so we continue from there. All we have to do is just do the integral, and that's simply 5 times 10 to the power 6. And then, of course, we do the integral of, I believe it's 0.2, and that's tau, minus 5,000 divided by 2 tau squared. And then we substitute 20 in here, we substitute t and plus 5, and we'll end up with the equation for that particular third range. And that will be 5 times 10 to the power 6, and of course 0.2 t minus, I believe, 2500 t squared. And the whole thing in here, we can just say negative 0.2 times 20 microseconds. So of course this one here is because it's 20, just to make sure that this has to be multiplied by 10 to the negative 6, so that we're dealing with seconds, so this will be times 10 to the negative 6. All right, so that will be 0.2, okay, times 20 times 10 to the negative 6 minus 5,000 divided by 2 times 20 times 10 to the negative 6, the whole thing squared, and plus 5 as well. All right, so if you do a little bit of algebra and you clean it up, you'll end up with this particular equation. So I went ahead and I did this algebra. There's a little bit of a missing parenthesis in here, somewhere in here. Anyway, so you'll end up with this particular equation. Okay, so let me just go ahead and just write it. So this equation tells me that what we have is negative 1.25 times 10 to the power 10 t squared, that's also in the negative, plus 10 to the power 6 of t, negative 10, and that's for the range when t is between, I believe it's 20 to 40. So that's 20 all the way to 40. Okay, so now we're not done yet. So what we have to do is we have to do the next stage in here. For the next stage as well, we will be integrating 0, but what we need is we actually need to figure out the initial voltage basically at 40. And the way we compute it is by going in here and just substituting 40. So what we can do in here, we can say, well, let's substitute V at 40 times 10 to the negative 6 because of the microseconds, and all we have to do is just substitute that 10 to the 40 times 10 to the negative 6 in here, and we'll end up with the initial voltage for the next stage, which will be, I believe it will be 10 volts. All right, so for the next stage now, which is the final stage, what we have is we have T is typically, we can say that T is just simply greater than 40 microseconds. What we have is based on this particular equation, V is just simply 1 divided by C, well the integral of 0 is just 0, plus the initial voltage, which is 4 volts, and then what we do is we just go in here to this particular equation and we get 10 volts, okay, and that's for T is greater than or equal to 40 microseconds. So that will be the equation for V of T. I believe we finished all of the voltages, all the ranges. So again, what we do is we started with an initial voltage of 0 at t equals 0, and then we computed this equation in here. And what we did is we took that 20 and we substituted in that particular voltage equation that we got in here, okay, and that gave us the initial voltage for the next stage. We computed the equation for it, and also what we did is we applied the 40, which is the final value for this, and that will the final value for this stage will be the initial value for the next stage, and that will be the voltage in here. So now what we can do is we can compute now the power and the energy. All I have to do is just multiply I times V in each one of the ranges, and we can do the same thing with the energy. So let me just do that. So I went ahead and I just copied a cleaner version of these equations that I just came up with. And what we need to do now is we need to figure out what P times I times V. And again, based on passive sign convention and all the assumptions we've done, I should be using positive when I'm using I times V. All right, so I times V is here. So what we need to do is just basically come up with the different ranges in here. So for range, the T is less than 0, that will be 0 times 0, and just simply 0 in here. So T is less than or equal to 0. That will be 0 watts, because this is in amps and this is in volts. Okay, so the next range will be simply, we multiply the 5000 T times this particular value in here, and whatever we get is just simply in watts, and that's basically the power in terms of the range 0 to 20. And that will be exactly, I have went ahead and I computed these, so I'm just going to write them for you. So these are 5000 times 5000 T times 1.25 times 10 to the power 10 T squared, and that was just simply 6.25 times 10 to the power 13 T cubed, and that's basically for T is greater than 0, less than or equal to 20 microseconds. And the last, well, not the last range, the one before last, all we have to do is just multiply this by this equation, and we'll get the power between 20 and 40. All right, so, and that exactly will be 6.25 times 10 to the power 13 T cubed minus 7.5 times 10 to the negative 9 T squared plus 2.5 times 10 to the power 5 T. I believe that's negative 2, and that's also in watts. Okay, so all of these, by the way, are in watts. That's what we do. And the last one is just simply, well, it's 0 times 10, and that's simply just 0 watts in here. All right, so I went ahead and I computed this, and I cleaned it up as well. So I'll show you that cleaned up version of it. But before we do, let's continue by computing, for example, the energy. So as a reminder, the energy for a capacitor is half CV squared. So all I have to do is just to do that is just to take a look at the voltage in here. And the way we do that is we say, well, the first range, it will be 0. Of course, half of C, remember, it's like half of 0.2 times 10 to the negative 6 is just simply 100 times 10 to the negative 9. This is just simply half of C. That's basically what I computed in here for this particular example. Anyway, so half of C times V squared. So V squared for the initial value is 0, so we get 0. So that tells me this is T is less than 0. There's no energy, or there's no energy being stored. And the next one is, all I have to do is just basically take this one here and just basically multiply by this number and square it. So all we have to do is just say 100 times 10 to the negative 9 times 1.25 times 10 to the negative 10 times T squared, the whole thing squared, and that's basically whatever the equation that you come up with becomes T is less than 0, greater than 20 microseconds. And we do the last one, it's actually also the same, 10 to the negative 9, and that will be times negative 1.25 times 10 to the power 10, blah, 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 negative 10, okay, all the way squared. This is actually this equation here. All I have to do is square it, and that's basically for T is greater than 20 microsecond, less than 40 microsecond. And of course, the last one is just simply 100 times 10 to the negative 9 times 10 squared, which is 100, okay, and that's basically T is greater than 40 microseconds in here. These are all, if you think about it, these are, if we keep it in these equations in here, if C is in farads because we're multiplying by 10 to the negative 6 and V is in volts, all of these are in joules, okay? All right, so let me show you a cleaned up version of all these equations, and you'll see them here. Actually, I didn't write the equations for the W or the P because it's pretty straightforward implementation. More interestingly, I'm interested in the plots in here, so let me just focus on those. So again, what we were given this time is we were given the current across that. So what we do is we have a current source in here and a resistor and a capacitor, and that capacitor, I believe it was 0.2 microfarads, and we figured out that this is V and this is I, and we were told that this particular current source is actually providing this current. And if you take a look at it, both of them are linear equations. So initially we go all the way from 0 all the way to 0.1 amps, okay? And then it goes in here and it basically tells me this is how much it is in terms of amps as well. So there's a little bit of a pulse in here. You can think about it as a pulse. So this pulse generated the following. What it did, it increased the voltage slowly. Again, there's no sudden changes in the voltage. It increased the voltage slowly till it reached at 40 microseconds. It's reached some sort of a value, which is 10. That's what we see in here. And after it, it's just contained it. So if you think about it, this current in here, it provided some sort of a current. It charged the capacitor and it stayed at that voltage. That's it. The current becomes zero, as if it doesn't exist, as if I did disconnect it, and this capacitor in here just have 40 volt or 10 volts, sorry. After the 40 microseconds, it just have 10 volts across it. Now let's take a look at the power. So when we compute the power, we will end up with an equation. The different ranges will generate different equations. So the 0 to 20 will generate this particular equation in here. The 20 to 40 will generate this, and of course after 40 is 0, because I'm multiplying 0 by anything, it will be 0. So what we see is there's only positive power, which means that this particular capacitor is just consuming power, which means it's just storing energy. So it goes up and down, and what we do with this particular case, it actually stored energy, and at the 40 microsecond, this amount of energy, and which is actually right here, it will basically just keep it. And the way we can check that it actually stored energy is because it has a voltage across it. And in an ideal capacitor, there's no leakage, there's no nothing. This can stay forever as long as this capacitor is not connected. Of course, in real life, there will be some leakage, so you will see some currents, and the voltage will eventually drop to 0, eventually. All right, so you take a look also at the work or the energy, and what you will see is between 0 to 40, there's a bunch of energy that is being stored. And of course, if you do take the integral of that P that we have in here and you compute that voltage, what you will end up with is this particular value in here, which is, I believe it's 10 to the negative 6 microjoules or something like this, which is right here, okay? And that's what we do. Or 10 to the negative 6 joules, which is 1 microjoules or so. All right.